And thank you to Professor Casanova for inviting us and for the great hospitality here in Rio for 2 weeks. Today I'll give you a talk about retrieval augmented generation systems. That is a topic that is quite well related with the topic of the course you are attending. First, I'll tell you 2 words about myself and where I'm from. I'm from Italy, from CNR, that is the largest public research institution in Italy, and that has the mission of performing high-level research and promote internationalization. And I work in an institute that is located in Pisa, where there is the Leaning Tower, as you see from the pictures. And Pisa hosts the largest campus of CNR in Italy, and the campus has 13 institutes of different disciplines, covering different fields. And I belong to an Institute of Computer Science, of course, that is quite renewed in Italy and well positioned internationally for the level of the research. My group is a group of about 20 researchers that are listed in this picture. This is even if this is quite old and not all the members are represented, and some of them moved elsewhere. But anyway, the topic we are investigating are relating mainly to these 4 fields: information retrieval, and AI, and these 2 fields are strictly related to the talk I'll give today. And then there is an interest in highly distributed platform, in the sense that, of course, high performance computing and distributed resources is very important for both for many fields, in particular for information retrieval and AI, as you know. And another topic that is well covered by the interest of our research is the analysis of mobility data. And the talk that Chiara will give next week to you is related to this field. Okay, as Professor Casanova introduced it, my talk will cover the topic of a paper we recently presented at a major conference in Washington. The title of the talk is Improving RAG System, Retrieval Augmented Generation System via Sentence Clustering and Reordering. Here is the paper, and I don't know what something about your background. I don't know if you know what information retrieval means, and what were the more recent advances in this field that are strictly related to neural networks, to deep neural networks, and to large language models that are covered by your course. And so I prepared a few slides of introduction that shows mainly the progress of information retrieval towards the use of LLM for improving effectiveness in the retrieval of information contained in large repository. And so the first slide cover what is called as a classical information retrieval. I don't know if it was covered by one of your courses here during in your study plan, but anyway, classical information retrieval was and is still mainly based on 2 major tools. That one is inverted list, in the sense a way of representing the content of documents and accessing this content very efficiently. In an inverted index, we have a vocabulary of terms that are included in the document. We start from a collection of textual document. We extract from all the document, the collection, all the terms that are contained in the text, and we build a vocabulary with these terms. And then we build what we can imagine is a sort of matrix where on each row we have a given term, and on each column we have any information related to the presence of that specific term in a document. This allows to retrieve, given a query that is based on keyword, on a set of keywords. It allows to retrieve very efficiently all the documents that contain the terms of the query. And we have several models, several ways of weighting the importance of this term, and build a ranked list of documents that are ordered by the expected relevance they have for the query. Of course, one of the most popular model for achieving this ranking is what is called BM25. That is a very old algorithm, a very old equation that is represented, that consider the frequency of the terms in the query and the frequency and the inverse frequency of the terms in all of the document of the collection to compute for each query and document a score that allows us to sort the documents of the collection by this score and obtaining a ranked list of documents ordered by their expected relevance. Of course, I'll go quite fast in these few introductory slides, so please stop me if you need some clarification or you have some question, okay? This was classical information retrieval, and until the 90s was the only way of performing retrieval. Starting from the 19th, particularly in the second half of the 90s, information retrieval start to use machine learning for improving the effectiveness of the ranking process. In this case, we have the previous classical information retrieval system based on inverted list and simple lexical model for rankings, such as BM25, that allow us to compute a preliminary list of documents based on their expected relevance of the document to the query submitted by the user. And then we use machine learning to improve the ranking of the top scored documents, in the sense that we extract a set of features from these documents. The feature can be the score computed by BM25, but also other information. For example, if we are considering web documents, we can consider for each document the number of links that refer to the specific web page, or the number of times the specific web page was clicked by a user issuing these queries, and a lot of other signals that we can use to improve the ranking by a machine learning model that try to, on the basis of a golden standard, those we are talking about supervised machine learning, that try to infer from this golden standard the best ranking function that emulate the information and the ranking function that is hidden in the supervised data used for building the model. This was what the major advancement in information retrieval until the advent of deep neural network and the popularity of the deep neural network. And the thing changed on 2000, starting from 2017 with the introduction of transformer models. Maybe you know this picture that is referred to the paper that introduced a transformer models in 2017. And based on this architecture, there was one major achievement that was BERT, a large pre-trained language model that changed a lot of the state of the art in a lot of fields. In many fields of natural language processing and also information retrieval and machine translation. With this change, we started to talk about neural information retrieval, but for distinguishing it from classical information retrieval. Classical information retrieval was that one based on lexical models such as BM25 that we survived earlier. And the most important characteristic of a neural IR system based on pre-trained language models is that they can capture complex language pattern and try to devise to understand the semantics of the text. And so the matching of the document of the query with the document is not anymore based on lexical matching, or the fact that we use the same terms in the query and in the document, but is related to the semantic of this term that this term have in the text. And the transformer model with their contextualized understanding of the text allows us to adapt to different queries with a very good understanding of the meaning of the queries and on the meaning of the documents. And this we solved it in this way, what was before called as a semantic gap, that was the gap that distinguished the use of the language in the query and in the document, that was one of the most strong constraints of classical information retrieval. On the bad side, of course, this new technology of neural AR is more computational demanding. It requires significant computational resources, and so we started to use GPUs instead of normal processor, and also the representation documents and of queries is much more heavy, in the sense that also in both space and time that is required to code, to index, and to retrieve the documents based on the query. And another very strong constraint is that, as you know, deep neural network needs a lot of data set for training and fine-tuning. While in the case of traditional information retrieval, it was quite simple to operate effectively with less data and with relatively small training data set for machine learning. Now we need huge data sets and many supervised assessment for training the model and performing effectively information retrieval. And so on the first side, the use of pre-trained model, such as the one in BERT, that implemented the architecture of the transformer model coded in the paper Attention is All You Need, was the substituting the machine learning part of the that was devoted to score the document based on the feature, on encrafted feature built and extracted from the query in the document. We instead substituted this module with a fine-tuned transformer that learn from a supervised data set how to match, to measure, to score the similarity between the query and the document. And this was, for performing this task, it used the mechanism of self-attention that was introduced in the transformer neural networks. Of course, this model was very computationally expensive. And so what was done at the beginning was using still traditional information retrieval for retrieving for each query a small limited set of documents that are likely to be relevant for the query, and use the cross encoder and the large language model to score only this top K set of documents for reducing the cost, the computational cost of query processing. This is what happened with this use of these models, in the sense that we have here a plot that where in the x-axis we have the latency, the query latency, the millisecond needed to answer a query, and on the y-axis we have instead a MRR, which has a mean reciprocal rank, that is a measure of accuracy, of quality of the ranking model. So in the sense that more MRR is high, the more the model is able to put in the first position of the list the documents that are the most relevant for the query. As you see in this plot, we have at two extremes the standard lexical model of classical information retrieval, which is BM25, and on the opposite corner we have a cross encoder based on BERT, that is this pre-trained language model. Of course, these models this deep learning model allow us to solve the semantic gap, to understand the meaning of the text in the query and in the document. But as you can see, it is very high demanding in terms of time. For example, from solving a query with BM25 was very efficient. We were requiring only a few milliseconds for processing all the query and scoring all the documents. And instead, by using BERT, only for scoring the top 100, 200 documents by BM20, ordered by BM25, we need more 3 seconds and a half. That is not acceptable as for large-scale system. You can imagine that if we put a system like this on a web search engine such as Google, that has to process millions of queries in a very restricted time frame, this is not feasible at all. And so a lot of research started working on how to make this model efficient and fast. And one of the solution for improving these models, and so to obtain models that are both efficient in terms of computational resource use and effective in terms of quality of the results of the documents that are retrieved given a query, is using B-encoders, in the sense that in this case we do not have a full cross-attention mechanism that try to match and to interact all the terms in the document with all the terms in the query, but we use an encoder that is learned, of course, to encode from the documents from one side and the query from the other side. Since we do not have cross attention, we can encode offline all the documents, and we need to encode online at query processing time only the query. And given the encoder of the documents and the query, what we have is at the end of the encoding phase a vector or a set of vectors that represent the documents and the query. And in this case, the ranking is performed as a function between this core. The function that is most used is usually cosine similarity or some distant functions such as L2, the Euclidean distance between the vector representing the query and the documents. In this way, what happens is that the model, the deep learning models, learn a way of representing the concept in the documents based on their semantic. And so we do not have, for example, if we have two concepts of a mouse, the mouse that we use on the computer, and the mouse, the animal, the rodent, this concept are encoded by two different vectors that are quite far one from the other, because the semantic of these two concepts are very, very different. And what we learn is that if we perform a query such as, I don't know, mousetrap, the encoder of the query try to encode this query in the latent space in a position that is very close to the concept of mouse rodent and not, of course, to the concept of mouse computer. And this allows us to encode somehow the semantic of the text within this latent space and this vector that represent the document, the query. And the retrieval of given a query of the most relevant document becomes the task of finding the closest vectors in this latent space that is learned. And so the operation becomes a KNN operation that is classical in the database world or on the classification task, or for sure you have several examples of how to perform this task, this very common task. And what happens is that in the recent state of the art, this model based on B encoder are very effective and works not only on in-domain retrieval, in the sense to retrieve data that is very similar to the data that was used to train this model, but are quite effective, as shown in this plot, also in zero-shot scenarios, where we have a model that is learned in a supervised way on a data set, but is used to score and to retrieve the documents in for another data set. And this is very important, of course, because we do not have many large data set for training of this kind of model. Of course, indeed, we in the community we have only one that was provided by Microsoft. That is Microsoft Marco dataset. That was a very large dataset that allowed us to learn deep learning model, a language model for information retrieval. And but we can use also the models that is learned on this dataset on other dataset very effectively. And so this you see that the performance that are plotted on the y-axis are related to zero-shot evaluation in some benchmark. Instead, on the x-axis, you have in-domain evaluation of the MS Marco test dataset that is related to the data that was used to learn the models. And so with the use with the introduction of this BN code and the parallel advent of a large language model, what the information retrieval community was started asking is if we can change the searching paradigm and exploit the potential of this novel B encoders for semantic retrieval with large language models that allow us to have a deeper understanding of the text. And so from one side, we have with the encoder model an efficient way of retrieving documents that are relevant for a query. We have the possibility of encoding new documents effectively, and so to respect the freshness of the information when the collection document changes, so we can reindex and include the new knowledge in the index, and we can use reputable sources. That is really different from what happened with LLM, where we have instead a very simple, a very effective semantic match, the context understanding, natural language interaction, but we do not have the possibility of introducing easily new information. As you know, the knowledge that is included that is captured in a large language model is related to the data set that was used for the training. And so when we ask to LLM a concept that was new and was not present in the large collection used for their training, we have very commonly what are called hallucination, because of the large language model behaves as a stochastic parrots and try to build an answer without knowledge the concepts that are behind the query that was asked to the system. And so what we started asking is how information retrieval and large language model system can work together. And we can easily identify three important steps in which this interaction can be successful. One is of course query interpretation, where we can use an LLM to enhance the query by understanding in-text context. And here instead can use the refined query to retrieve efficiently the most relevant document from a trusted knowledge base that contain relevant information. Then we can also use both a system for contextual retrieval, where we use the information retrieval system to find efficiently the documents that match the query that was expanded, enriched by the LLM in the previous step. And we can again use the LLM to improve the ranking of this document by the contextual understanding that it provides, and using the semantic relevance instead, rather than just keyword matching as it was happening in traditional retrieval. Finally, we can have another step in which we can use LLM to improve the interaction with the user and ask the LLM to generate a response, not only a set of 10 blue links as happens in a traditional search engine, in traditional retrieval system, but instead we can use the LLM to build an appropriate response for the query based on the document that was extracted from the knowledge base. And this is exactly what retrieval augmented generation aims to do. In this plot, we have a very simple schematic view of a retrieval augmented generation system, where we have, you see, a query, and the query is submitted to a retrieval system based on the B encoder that enrich the query and extract from the index from the knowledge base a relatively small set of retrieved passages that are expected to be relevant for answering the query. And then we have a large language model that use this query and the passages and the snippet of text retrieved by the retrieval system to build, based on a prompt, the response that is finally passed to returned to the user. And this system can easily improve and somehow join the advantages of both worlds. From one side, we have the advantages of information retrieval system, that is the possibility of using trusted documents, of including fresh information quite easily. And on the other side, we have the advantage of large language model in understanding the text and interacting in a natural way with the user. So this is an example of a query and what is the processing that the retrieval augmented generation system makes when it receives the query. For example, the query is what is the color of Napoleon horse, a very standard query. You see that this query is passed to the two subsystems. First, it passes to the retriever. The retriever uses a B encoder to extract from a knowledge base a set of documents that are possibly relevant for answering this query. You see in the large box, green box, the retriever chunk and the chunks of the text that are retrieved by the retriever. And in the first chunk, we have Napoleon Bonaparte horse Marengo was renewed for his striking gray color. Marengo named after a significant battle victory, blah, 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 blah. Instead, we have another document that talks about Napoleon and horses, and but is not strictly relevant for answering this query. And the text says that Josephine, Napoleon's first wife, had the preference for horses with elegance. Her favorite was a chestnut-coated horse. Finally, in the third document that is retrieved, we have a document talking about Napoleon, but not speaking of the horses. That is not so relevant for this query. These documents that are retrieved from the knowledge base are passed to the large language model that is prompted and asked to answer the query. For example, we use a very simple prompt. We'll say answer based on the following information, and we provide the LLM with a context that is given from the chunks of document of text that are retrieved by the retriever, and we ask the LLM to answer the query. What is the color of Napoleon horse? And in this case, of course, the LLM will understand which are the relevant passages of this document and will answer that Napoleon horse color was gray. And this is the effect how RAG, retrieval augmented generation, works. Oh, we have those enhanced with respect to the use of traditional AI system or the use of LLM for answer this kind of query. We have the possibility of combining the strength of retrieval-based and generation-based model for generative responses. We have reduced the hallucination because we do not ask to the LLM to extract from his weights the knowledge that is needed to answer the query, but we provide this knowledge direct to the LLM from external sources that are also possibly trusted, and we can also refer in the answer which is the source of the from where the answer was extracted, and so we also improve the trustfulness of the system with respect to the user. And of course, we can easily integrate up-to-date databases, up-to-date information to reflect the latest information and the dynamicity of information. But in any case, we provide contextual realism by the use of a large language model, and we can provide coherent, contextually appropriate responses to the query. We partially solve the task of scalability in the sense that we use an IR system that is efficient, and we can index large data set and process complex query and reduce the computational overhead. And we use the LLM only for a quite more simple task, that is understanding which is the relevant passages and the building, generating the final response that is returned to the user. At last but not least, we have an improved flexibility in the sense that this kind of system can be adapted to various domains very easily. So we can build a rack system that is specialized on, I don't know, on sports, and the rack system that is specialized on historical questions, but only changes the knowledge base that is behind, that is used to feed the large language model to the and so we join and we combine the advantages of both worlds. Anyway, there are also many challenges in the sense that that is not so immediate building an effective, efficient rack system. And in the following, we will see what are the challenges and how we can deal with them, as we did in our work. The challenge, let's analyze this list of challenges. The first challenge is that of course, we need I recall from the AR system, in the sense that we have to build a retrieval system, a retriever that is effective and can feed the large language model with pertinent information and the relevant information. Because if we provide the LLM with wrong answer and with wrong information, also the final response will be, of course, wrong. And of course, another aspect that in any way is granted by the use of B encoder and the retriever based on B encoder dense retrieval system is that we need to have a high recall. We need to solve the semantic gap between the language that is used in the query and the language that is possibly used in the documents that are relevant or not relevant for the query. Okay, and so this, as we introduced before, the aspect of recall and semantic gap is solved by using a B encoder, state-of-the-art B encoders, and in this B encoder we can use a similarity search system that is very efficient to answer the query, and because the queries and the document are encoded in the same latent space, and the retrieval is performed using a KNN search within the collection document embeds that represent the information in the knowledge base on the data set used by the RAG system. We have again this, but we already. Then we have other challenge that we have to deal with, in the sense that, of course, the scope and the text window of LLM is not so large, even if the new system are more and more large than the previous generation one. But in any cases, it is proven that LLM are not good at reading too many chunky documents, in the sense that if we provide the LLM with too much context, it often is not able to identify very neatly, very effectively where is the relevant information that has to be used. And so there are several studies that address this question, this research question. And these studies shows that the number of documents that we have to provide to LLM to improve, to optimize the effectiveness of the final answer is varying on the basis of the large language model used, and also on the basis of the data set that we want to use. In any way, a number that range from 5 to 20 is a good windows for providing context to the large language model. Anyway, we have to fine-tune this number on the basis of the specific data set that we use for the RAG on the basis of the characteristic of the queries that are given in input and that are important for the system. Another challenge is that the user model may be not suited to model LLM use of input information. What does this mean? This means that the user model that is behind information retrieval system is very simple, in the sense that the system tries to sort the set of documents that are likely to contain the answer on the basis of their expected relevance for the query. And so when we go on Google and we type a query, we have a set of results, and these results are ordered by the expected relevance of the document for answering the query. And also the user model is very simple. That it means that the documents that are listed first are the most important for answering the query. We are not sure anyway that this happen also for LLM. And so we have to try and to understand what it happens. And one paper that was lost in the middle showed that LLM are different from standard user, in the sense that they proved with a quite simple experiment that were performed by shuffling the order of the documents that are given in input to the LLM, and they proved that the LLM focus the attention mostly on the previous on the documents on the first position, and the document in the last position, and disregard somehow the documents that are in the middles. And so this is quite different from what happens on traditional information retrieval system, where we have, of course, the larger importance of document in first position, but we do not have a focus on the last on the documents that are sorted, that are ranked the last in the one returned by the system. And so this is something that has to take in consideration, and the respect that LLM have to be considered differently from user in providing the set of documents that contain the answer. Interestingly, we note that I found that there was some works that try to understand which is the right number of documents to provide to the LLM, and try to understand if there is a positional bias on the documents that are that are given as a context to LLM, no one tried to understand if there is a specific order of importance of the document that that enhance the accuracy. And this was what we tried to do in a specific context in our work. One of the last problem of RAG is that the unit of information is quite different, in the sense that the retrieval system works with documents, or even in some cases we can split the larger documents in sentence, in paragraph, and index this paragraph. But instead, the large language model are more strong in understanding the context that is provided in single sentences. We have a specific windows of tokens of words that is considering the context from the large model, and at the end, the large language model works with tokenized words that represent somehow this context. And so what is important is that once we use the retrieval system to extract from the knowledge base the set of documents that are likely to be relevant to answer the query, we perform an additional step to represent and to split this document in separate sentences that can be more likely, more easily understood and considered by the LLM. And this is done with very simple natural language processing tools that resolve co-reference, that perform co-reference resolution, that means replacing pronouns and generic term with the entity mentioned in previous sentences. For example, in the first chunk, you see that the second sentence is Marengo, named after a significant battle, victory, blah, blah, blah. And this sentence does not have any relevance in the context of the query, on the content of the document, because it misses a specification. For example, that Marengo was the name of Napoleon Bonaparte horse. And so what we perform is using this quite simple standard NLP tools to split the sentences and make each sentence as self-contained, and so resolving any reference to a subject that was mentioned in a previous sentence, and that makes the understanding by the LLM easier. That's way. And what we asked in this work is how we can leverage the representation spread properties of the document that is provided by the encoder to improve the effectiveness of the retrieval augmented generation system. This was suggested by a lot of work that tried to analyze how these deep learning models encode the text in the latent space, in the sense that these studies proved that the latent space is not a uniformly distributed space, in the sense that the entities, the documents, the text chunks in this latent space are not distributed uniformly in this space, but there are regions that are more dense and regions that are less dense. And the only thing that during the learning the model tried to do is moving close concepts that are close and moving far concepts that are far from a semantic point of view. And thus this results in a space that is not indeed uniformly distributed, in which the vector, the embedding that represent the documents are not uniformly distributed. And so we consider one specific kind of retrieval task, which is a multi-turn conversation, where in the sense we have not single queries, but we have a conversation between a human and an intelligent system. And the conversation is multi-turn in the sense that the user starts providing one query, one question, and the system can answer, and the user possibly use this answer to understand more about the topic he has in mind, and this is an example of conversation that is Red Bull bad for you? And the system will provide some information. The second question by the user is, can it kill you? And the dialogue continue with additional information that are asked by the human, such as how much can you drink in a day, and so far. And so we have a sequence of utterance of a question by a user and a set of answers that are provided by the user. What is evident from this plot is that if we consider the embedding that represent for each conversation, which in this plot we plot the 1, 2, 3, 5 different conversation, and we plot the question that are asked by the user that correspond to the colored circles, and the documents that are relevant for answering this question that are plotted in this plot as colored crosses. We see that there is some sort of structure in this latent space. There is some locality, in the sense that the sequence of conversation utterance and their relevant search result are clustered. And so looking at this plot, we asked if it is possible to leverage the similarity among retrieved documents to improve the effectiveness of the RAG system, in the sense that can we use clustering to improve the quality of the results that are generated by the retrieval augmented system. Can we understand which is the best order to provide the LLM with the context, the contextual information, in order to make the LLM answer in the best possible way to the user queries. And this is what we did by considering this, by designing this architecture that is a standard retrieval augmented generation system, where we inserted additional components. And you see, as before, we have a query, and the query is given in input to the retrieval system. The retrieval system extracts from a knowledge base a set of passages of text chunks that are expected to be relevant for the query. We use this natural language processing tools for coreference resolution and so on, to split these passages in short sentences that can be considered in an atomic way by the large language models. We perform an additional re-ranking of these sentences for identifying the sentences that are the most relevant for the specific query. And then we provide some different way of giving this set of sentences, a fixed set of sentences, in input to the large language model for response generation. What we did is that we clustered this sentence on the basis of their semantics by using a clustering algorithm in the latent space, as we showed in the previous slide. And then we try to understand which set as a reordering strategy is better to enhance and to optimize the quality of the answer that is generated by the LLM system, in the sense that we given the data set that contain all the relevant document, all the information about the conversation, we provide the LLM with different order in which we order in different way the sentences that are considered the most relevant for answering the question. And we measure somehow, we will see in the next slide, how this different order affect the quality of the response. This is what I just say in words. Of course, this was not so easy because it's relevance in the a human-based judgment, and we do not have a direct way to understand, to assess which answer obtained by LLM is better, in the sense that if we ask to Professor Casanova to judge if answer A is better than answer B, Professor Casanova can say that A is best, and I instead can believe that B is better than A, in the sense that is the relevance is not objective, and we need to remove all the possibly all the bias from this kind of assessment, and that is very difficult to perform. And what we did for trying to assess in a quite fair way the quality of the answers that are returned by the LLM on the basis of the different input that is provided, and we remember that the input is varied on the basis of the different clustering strategies that we used. We have to understand, to have a possibly principle of the way to understand if an answer is better of another. And what we did to obtain this information is using again a large language model. And specifically, we use ranked vicuna, that is a large language model that was fine-tuned for a ranking task, and it's based on Llama 2. And we asked to rank vicuna. We provided this rank vicuna with all the answers that were obtained by the different way of ordering the input information provided to the LLM. For every ordering strategy, we obtain a given answer from LLM for each question. And of course, we have a different different answer provided corresponding to different permutation of the input, and we have to understand which was the best. And what we did is we asked to rank vicuna to rank again on the basis of the quality the answers that were provided by the LLM in the previous step. Of course, we remember that you remember that we have a direct proof of bias of positional bias in LLM, in the sense that if we provide, we understand from the previous work that was lost in the middle, that the information that is in the middle of the context that is passed to the large language model is the one that is less likely to be used to be considered relevant by the large language model. So what we did is that for every test, we repeated every test several times by shuffling randomly the position of the different answer in the input. And so in order to obtain, if possibly, to remove the positional bias from the answer of the large language model. And at the end, we try to understand which strategy that is represented in this plot by a different color was, in the average, the best for ranking the documents that are passed to the LLM. And so finally, we try to use all this infrastructure, all this machinery to investigate the following three research questions. The first one is what is the best cluster order strategy, in the sense of that, as we said before, we cluster all the passages, the sentences retrieved by the retrieval according to the self-similarity by using k-means on the embedding that represent these sentences. And so using this cluster strategy, we obtain for each query a set of cluster, each one contains some sentences. And so we try to understand which is the best cluster ordering strategy, so the best way of providing the LLM with the information at the cluster level, and also what is the best ordering strategy within the same cluster, in the sense that, of course, we can vary the order in which we provide the sentences belonging to each cluster, but also the order in which we provide the LLM with the sentences within the same cluster. And the research question is if we can devise a strategy that enhances the effectiveness of the RAG system with respect to other methods than baseline. So we performed this task on the basis of this collection, which provide us all the supervised assessment of relevance for this query. And what we did is that we answer to this question, and we understood that the best way of providing the cluster order strategy is providing the cluster selecting descending order of similarity with the query. And so we provide the LLM with we order the cluster on the basis of their similarity to the query, and we provide this cluster to the LLM on the basis of descending similarity with respect to the query. And we find that instead the worst solution is using the opposite order, in the sense that if we provide the cluster in ascending from lowest to highest order similar to the query, we obtain the worst quality of the final result generated by the LLM. For what regard the second research question, we instead found that if we select the sentence by aggregation order given by a hierarchical clustering, in the sense that we provide again the sentence within the cluster in order that maximize the similarity to the query. And this was, again, the strategy, the best strategy. This shows all and summarize all the result. You see in each cell 3 numbers, and in these 3 numbers we have reported the number of times the models, the strategy on the row, on the column, sorry, outperforms or the strategy on the row, in the sense that if you look at the first top most cell in the right, you see 66 to 43. That means that in all the experiment for 66 times, the best clustering ordering strategies was resulted the winner with respect to the strategy A, that is top retrieved passages, using only the top retrieved passage to provide to the LLM. In 2 cases, the quality assessed by the LLM rank Vicuna was the same, and so we do not have a clear winner. in 43 times instead we have that the top the ordering the passages by the order of retrieval rank retrieval was best that using our best clustering order strategies. And so at the end we compare all the possibility in this table, and at the end we have that overall our proposed approach was the winner, and with a total of 251 win, 13 tie, and 180 loss in the comparison and the direct comparison with the competitor. So all the tests were statistically significant, and so the best clustering order strategy that we proposed was the clear winner of this turnaround test. And so now we are to the final consideration. The final consideration is that, as we understood, is the quality of responses generated by the large language model is affected by the order of retrieved information within its prompt. And this is proved also by the loss on the middle paper, but we proved also in our paper, and we show that by properly providing the context to the LLM can result in improvement up to 54% over providing a random ordering of sentences to in the context given to the prompt. And so this is our finding in this case is in line with the other work in the literature, but in any case our finding was novel in the sense that all the other works tried to understand what are the limitations of LLM in understanding the context given in the prompt, but didn't investigate what is the best ordering of giving the information the prompt, as we did in the case of conversational user conversation with the system. Another consideration that is descend typically by the behavior and by the context, they can contextualize the information that LLM try to understand is that coherent, fluent, and well-structured text are critical factors for successful human communication, and the same also applies to LLMs. If we provide, as we did, the LLM with a set of with a content that is well organized, well structured on the basis of the similarity to the query, we obtain a better result that giving the same input in an unstructured way that introduce more noise to the LLM input. We have, of course, also even some limitation in the sense that the current experimental evaluation is limited to a single data set because of the conversational data set that we use. It is not huge. It contains about 100 conversations, and which conversation is include about 10 queries. So we have in total about 1,000 queries for this evaluation. This is not so extensive, and of course, future work is understanding if this aspect of clusterization is important even for other tasks that are related to retrieval augmented generation, such as question answering or other different retrieval tasks that are important in our domain. And that's all. And so if you have a question, of course, I am available to answer.
Okay, thank you, Professor Raffaele, for your clear presentation. The students might be able to access it later on because I'm recording here. I'll stop recording and we can move to the questions. Okay.